Hello, my name is Mark Ryan, and on behalf of everyone at Shepherd Color, I'd like to thank you for joining us for the webinar all about Arctic infrared reflective pigments. Shepherd Color has a long history of producing colorants for the use in specialized applications, and one of those is in highly durable building products. These Arctic infrared reflective pigments are an extension on that technology. So what does this technology do? Well, in simplest terms, you can think of it like this. If you want to avoid getting a sunburn, what do you use? You use sunscreen. And if you want to protect building products, coatings, and plastics from the degradation of the sun, from the thermal degradation, you can use Arctic infrared reflecting pigments. Arctic is a trade name that we use at Shepherd to denote these infrared reflecting pigments, and this is Frosty, our mascot for this product line. So what does this technology do? Well, here we have an example of two 3D printed model houses. So these are identically produced ABS plastic, and on the left-hand side, we have standard pigmented materials, so representing the roof and decking materials. And on the right-hand side, these are pigmented with the Arctic IR reflective pigments. As you can see, they're both very dark in color. These houses were put outside in the sun on a bright, clear, hot day. And what we can do is look at them in the visible. We can also look at them with a FLIR imager. So this is using the far infrared thermal imaging wavelengths of light. So coming off of the standard pigmented roof, you can see that it is much hotter than the Arctic infrared reflective roof, even though they're the same color. And we can look at this qualitatively. We can also look at it quantitatively. So the standard pigmented roof actually has a surface temperature of around 67 degrees Celsius. Meanwhile, the Arctic pigmented roof of the same color is 7 degrees Celsius cooler than the standard pigmented roof. This is what the Arctic technology does, is for the same color, you can have a lower temperature when you're exposed to the sun. And this is useful in a number of applications. One of them is PVC siding. So this is in a lab setting. We have two PVC plaques of the same thickness, one pigmented with standard black pigments and the other pigmented with IR reflective pigments. What we did then is we put on a simulation of the sun, a heat lamp bulb, and over a few minutes, as these pigmented plaques absorb the light coming off of the bulb, you can see that the standard pigmented chip starts to warp, and that's because PVC will thermally deform if it's exposed to higher temperatures. So even though they're very similar in colors, you can have a PVC plaque that is much more dimensionally stable using the Arctic IR reflective pigments. So how exactly does this technology work? Well, we're all familiar with how the sun gives us light so that we can see things. The sunlight that we use to perceive colors is from 400 nanometers to 700 nanometers. And those are the visible wavelengths of light. We're all familiar with those. We're also familiar with the UV wavelengths of light because we know that those are the ones that cause the majority of the degradation of materials through the breaking of chemical bonds. And then past 700 nanometers, past the visible spectrum, is the near infrared wavelengths of light. So the sun is not just putting out light for us to see, it also is putting out a lot of energy from around 295 nanometers all the way out to 2500 nanometers. And if you integrate the area underneath these curves, you can find that there's a few percent in the UV, although it's very damaging. And roughly the rest of the sun's energy is split between the visible wavelengths and the near infrared. So the key is that we can't perceive these near infrared wavelengths. These are invisible to our naked eyes. So this graph is actually looking at the reflectance curves for some common pigments. So on the vertical axis, we have reflectance, so more reflective pigments, like a white pigment here in the visible, like a standard titanium dioxide. will reflect most of the sun's energy. Meanwhile, for a dark, aesthetically pleasing color, you'll have low absorption or low reflectance, high absorption, so you can have a black, dark color. So this would be a reflectance curve for a standard black pigment like a carbon black. So you can have reflective in white or absorbing and black. And those are what's happened. That's how we perceive the colors in the visible. But once you get in the infrared area, these two pigments continue on with their basic nature. The titanium dioxide still reflects and scatters away the near infrared energy. And standard blacks continue to absorb just like they did in the visible, and they have very low reflectance. So we can, just as we were looking at the sun's energy, we can compare these graphs to the amount of energy the sun is putting down, and then we can come up with a number for how much of the sun's energy these pigments are reflecting. And that's called the total solar reflectance. So the titanium dioxide will have, in a plastic or a paint, will have around 80% reflectance. Meanwhile, a carbon black or standard black will have about 5% reflectance in the visible and all the way in the infrared. So it has around a 5% TSR. The science behind the Arctic infrared reflecting pigments is that they absorb in the visible wavelengths of light so that they're dark, they're aesthetically pleasing colors. But once they get into the invisible infrared wavelengths of light that our eyes can't perceive, they start to reflect and scatter that light back out of the film and plastics. So what you have is the aesthetically pleasing dark colors, but you have the reflectivity of the more bland white pigmentation. So whereas the pigmentation, the white pigment will have around 80% reflectance for TiO2 and 5% reflectance for carbon blacks, these infrared reflecting blacks will have a TSR between 25 and 30%. So why is that important? It's important for a number of reasons. We saw with the PVC plaques that the absorbing of that infrared light heats up materials more and causes deformation of temperature. And we can see that, the sun coming down and it's bringing down the UV visible and infrared wavelengths of light. With standard pigmentation, the materials are holding on to a lot more of that energy that the sun's coming down. It's only reflecting away only a small portion of that, especially for dark colors. So that means that what's going to happen is that material is going to get hotter itself, but it also has knock-on effects for the material, for the area around the material. The air blowing across that material is going to pick up that heat, and that can manifest itself in the bigger picture as things like urban heat island by heating up the air around black parking lots and dark colored materials in the cityscape. And also, once the energy is absorbed in the material, if it's not moved away by that convection or it doesn't heat up the material itself, it's going to be emitted as long wavelength infrared light. Those long wavelengths of light that we saw in the FLIR imaging earlier get trapped eventually in the atmosphere because of things like carbon dioxide. And those wavelengths of light will heat up the air and lead to things like the global warming. So if you can, what you want to do is reflect away as much of the light initially as possible. So that keeps the material cooler. It has less energy to be emitted in the far IR wavelengths, and it heats up the air less around the building so that you have less urban heat island effects. So that's what we think Arctic is a very good for a number of applications in the building products. And this use has been codified in things like the EPA Energy Star program for cool roofing, and also for some of the LEED programs for points for when you're building a new building. But we see it as a big part of sustainability. As we saw, it can help keep the air cooler around cities, reduce the urban heat island, which less urban heat island makes cities more livable and also improves air quality. If the materials in the roof stay cooler, the building has potential to stay cooler, and that can lead to the reduction in energy demand for cooling, which reduces the amount of energy needed to be used and burned from coal or natural gas, which reduces carbon dioxide emissions. And that all leads to a better environment and all around. So we see this Arctic pigment technology as being good for individual products and also for sustainability on the whole. Of course, this is part of our product lines that have been used for decades in high performance building products like pre-painted coil or PVC or other applications, uh, other polymers. What we have here is a PVDF panel, fluoropolymer with an acrylic binder. This is a standard test that we do. So this is the mass tone. It's one of our early generation IR reflective blacks in mass tone by itself, and then tinted off with some white to show the expression of the color. As you can see, the mass tone color and the tint color were covered by a clip here and then put down in South Florida for 17 years. And so this represents what it would look like if it weren't exposed to the sun, and this is exposed to the sun. As you can see in this high performance resin system, these high performance pigments are giving durable, lasting color. This infrared reflecting property is inherent in the pigment chemistry. It's not an additive or anything like that, and it doesn't wear out over time. So the reflectivity that you get initially is inherent with a pigment and will be there for years and years. So these are the kind of pigments that give the paints and coatings and plastics manufacturers the ability to have products that have life cycles of over 20 years. Sometimes they have 40-year warranties for these commercial products. And as we saw, standard black has around 5% reflectance. These infrared reflecting blacks have around 25 to 30% reflectance. So you're getting a 5 times increase in the total solar reflectance. And that's important because you need all that reflectivity to help keep material cool, but also to meet regulatory and code requirements for materials. We talked to a number of different people in the industry that have used a number of different pigment technologies, and they have told us that Shepherd Color is the leader in IR reflective and low heat build-up pigments. And that's because we've been working on them since the early 1980s for use in building products. So over that time, we found a number of keys to success. One of them is pigment selection. So definitely finding out which pigment is the best for your application. And then there's when you start to match colors and mixing pigments, how those pigments interact. And then, of course, once you put them into paints and coatings, then also into plastics, there's application variables associated with film thickness and other attributes. Then there's also issues with contamination. Even just small amounts of standard pigments can cause a radical decrease in the total solar reflectance of a color match. And then finally, there's measurement issues there's a number of different ways and techniques of measuring the TSR, and those become very critical when you're especially looking at meeting specific requirements for codes and rules. But the interesting thing is that this is beyond just color matching, where you mix colors together and get a color that you can see with your eye. A lot of these interactions are happening in the IR wavelengths that are invisible to the human eye. So I like to say that working with these pigments is kind of like color matching blindfolded. But we can definitely help you out with that. Our tech service lab has spent the last 20 years doing probably by now tens of thousands of color matches with this Arctic technology, and I've learned a number of tips and tricks that can help you get the highest performance that you're looking for in these infrared reflecting pigment systems. At the core of that is that we have a number of different possible pigments that you can use for your applications. I like to call it the black rainbow of options, though. Even though they all look like black pigments, they all have subtle different properties. And these come down to basically it's a triangle of 3 different properties that you have to kind of trade off: is the reflectance, how high of a TSR you want to have, the mass tone color, how deep of a mass tone black you have, and then the tint strength. So then, depending on the application that you're looking to fulfill, what requirements you have, we can guide you with the best pigmentation for that application. And by the Black Rainbow, we have at least 10 to 15 different products that you can use in these darker colors to help get you those aesthetically pleasing colors with the most reflectance, or in the tints where you're making lighter colors for the vertical surfaces. We can suggest ones for that. So please contact your Shepherd representative, and we can help you guide you to what product to use in the Black Rainbow. So we not only have our Arctic pigments that we've been talking about today, we also ally this technology with our Dynamix easily dispersed pigments. So what that means for you is that you can take this groundbreaking pigment technology, Arctic technology for cool pigmentation, and what you can do is incorporate it very quickly into new resin systems. Dynamix is primarily used in coatings applications because it removes the time-consuming and variable steps of pigment dispersion. But it's also used in plastics for high-temperature applications and for thin films, laminates, and fiber applications. So what we allow you to do here is take this infrared reflecting technology, incorporate it very quickly into prototypes in the lab, and then know that because of the consistent dispersion properties of the Dynamix, you'll be able to scale it up through small plant and then large plant production, or even be able to ship the formula around the world and know that you'll get the same performance no matter what. So this is some of the innovative uses of our products. This is an advertisement from India where our local partner is using these infrared reflecting pigments in seat cover replacements for mopeds and bikes. It's a very large industry over there. And what they found is that these infrared reflecting pigments have a number of different properties that make these seat covers much better. They sell them over there. They found that because of the infrared reflecting properties, the standard seats stay cooler. I know they have a red, a blue, and a green here, but most of those seats are actually very dark and black in color. One of the other things they found is that, as you can see here, they're touting a 3-year warranty. What they found is that the standard seat covers pigmented with standard pigments only had about a 1-year service life, but they were able to extend that to 3 years. But really what they're selling it is that by having a cooler seat, you're going to sweat less while you're riding your moped, and more importantly, your girlfriend riding with you will be more comfortable also, which I thought was an interesting way to sell the pigment to this infrared reflecting technology. And also because there's less sweat involved, there's less chance of slipping and sliding on the seat. So I thought that was an innovative use of the pigment technology outside of building products. But definitely building products are the biggest use of the technology. But we also have a very, what I consider a moving testimonial from over in Europe, where a number of coatings were applied to agricultural buildings to help reduce the temperature in the buildings. As you see, the infrared reflecting pigments have more reflectivity, it's keep the materials cooler. And in an agricultural sense, especially when you have livestock in the building, that increases the animal welfare. But also for things like happier cows give more milk, and cows aren't happy when they're hot and sweaty. So these pigmented roofs help keep the cows cooler and more productive. And then also, instead of they don't have to use as many utilities to help keep these barns cooler. So that I thought was an interesting use of the technology. They concentrated on 4 different colors for the application. These were, as you can see, from the standard commercial coating to the IR reflective one, for a wide range of colors, they were able to get a much higher reflectivity. So they can also be used beyond building products. The latest use of this IR reflective technology is in plastics. So regular standard black plastics, because of the IR absorbing properties of the black pigment, can't be sorted by the automatic equipment on the recycle lines. So this Arctic infrared reflecting pigments is helping sustainability by improving the recyclability of plastics. So we think these Shepherd Arctic infrared reflective pigments are an example of Shepherd's brand of having more expertise in these critical pigment technologies. Because of the black rainbow, the wide range of pigments that we have, you can get better performance out of your materials. And we think that because of this expertise and this better performance, you are able to get the best value for when you produce your own unique products. So what do you think about the technology? Where do you think that we could possibly go from here? We'd like you very much to contact us. As we've said, we can put you in touch with a Shepherd expert that is local to your market, and they can walk you through what would be the optimal product for your application. The best way to probably reach out with us is to reach out to us at our website at shepherdcolor.com and fill out the customer contact form, and we'll contact you about the use of these infrared reflective Arctic pigments. Once again, my name is Mark Ryan. On behalf of the Shepherd Color Company, I'd like to thank you all for joining us today. We did end up getting a number of questions that I wanted to kind of address right now. Can the pigments increase the longevity or quality of the coating? That's one thing it's hard to quantify, but definitely what we've heard back from the marketplace is that because the materials stay cooler, degradation is often driven by temperature. So if you can keep the material cooler, it's going to degrade less. Kind of a knock-on thing to that is also as things heat up, they expand and contract. So the potential is for materials made with IR reflective pigments is that they won't expand and contract and pull out fasteners. So that is one potential benefit that you could get from using the infrared reflecting pigments. And then what protective values do they add to the coatings? Largely, these are all the same kind of innate CICP, complex inorganic colored pigments that we've been making for decades. So they bring along all the durability, the UV stability, the resistance to acids and bases that you would expect from the standard standard CICPs that have been used for over 60 years now in high performance coatings. What are the cost benefits of the value of the pigments? Definitely, you can expand into new marketplaces. With a lot of building products, you almost have to use cool materials in them right now. The other thing is that the pigments the Arctic reflective pigments are on par with the other standard high performance pigments in the cost of them. Definitely, if you're coming from a carbon black based coating, carbon black is has a much lower density than these IR reflective pigments, and the use rate is much lower. So when you are going from a standard carbon black coating, pigmented coating to a infrared reflecting black coating, you really have to change a lot of the pigmentation parameters. It's hard to do you have data for saving energy between normal versus IR pigment when those are applied to coil coatings? There has been some work done on a number of different houses and then also on schools looking at the energy savings. It's very, very difficult to get exact data on this because it's usually houses have people in them and they live different kind of lifestyles. They set points are different. There's even been some schools where they try to do some standardized testing, and it's very difficult to come up with definitely a quantifiable number. But the EPA Energy Star cool roofing program and other applications have in aggregate found that it does save energy. It's just hard to quantify exactly how much. How many color pigments with IR function is Shepherd supplying? We have a whole range of pigments that we call our Arctic pigments, from our blacks all the way through our yellows and all of our colors in between. Where the biggest gains are to be made are in the black pigments, where you can go from a 5% reflectance for a standard black to a 25% reflectance for an IR reflective black. Yellows are inherently more reflective. Greens and blues are kind of in between. So for our Arctic line, we picked the most reflective of each of the pigment classes and labeled those Arctic. But when it comes to formulating colors, getting the best black pigment in there, and then also we have a number of other green pigments that are optimized for IR reflective properties. The heat stability is largely on par with all of our other pigments. So, over around 1,000 degrees Fahrenheit, the blues are stable up to 2,300 degrees Fahrenheit. So the same heat stability that allows them to be so inert and so stable. What range of IR wavelengths is reflected? Specifically, we're talking about the near infrared, so from around 700 nanometers out to where the solar light kind of falls off around 2,500 nanometers. But most of that energy in the near infrared from the sun is from around 700 out to around 1,200 or so. That is where a lot of that energy is. We're talking about specifically about the near infrared wavelengths. We're not talking about those far infrared wavelengths that are used for the FLIR imaging. Those are, around keeping the terms the same, around 10,000 nanometers for a room temperature object. So that black body radiation really doesn't play into the use of these pigments. Can they be used in glass? Yes, they definitely can. The standard pigments for these are pigment brown 29 iron chromites that have been used in glass enamels for a long time. Getting the IR properties specifically optimized is the key for the use of these in glass. How many degrees could we save when we take Arctic IR pigments instead of normal pigments? So the kind of the rule of thumb is, if you look at the ASTM E1918 test method, that is called the SRI calculator. Inherent in that ASTM is a model that looks at kind of the theoretical surface temperature. If you look at a total solar reflectance value, an emissivity value, and then a wind movement number. If you kind of play around with those, what you can find is that for most colors, going every percent change in TSR gets you about theoretically up to 1 degree Celsius change. So if a standard black is 5% reflective and a Arctic IR pigment is 25%, you've got a delta there of 20% reflectance, which should give you about 20 degrees Celsius change. But that would really be about the maximum difference that you could get. That would be for a bright, clear day with very low wind. Usually there's a lot of particulates in the air. That's looking at, I think, over about 1,200 watts per meter of sunlight. So that would be an extreme situation, but that's the theoretical max that you'll get between a standard and an infrared reflected pigmented. How many IR pigments of Shepherd color can be used in powder coatings? All of these pigments that we've been talking about are excellent performers in powder coatings. They have low resin demand. They have excellent opacity. They have the infrared reflecting properties. They make excellent pigments for powder coatings. Does the blending of infrared reflective pigments and non-infrared reflective pigments have a benefit, like a lose performance but lower cost? What we found definitely, and I mentioned it earlier, kind of with the contamination, is that the inclusion of even a small amount of non-infrared reflecting pigments greatly degrades the overall reflectivity of the system. So if you take carbon black and add just even a tenth of a percent on pigment basis to an infrared reflecting black, you're going to reduce the reflectivity by over half. It doesn't take very much, especially of a very strong pigment like carbon black, to reduce the reflectivity. Do infrared reflective pigments offer benefits for particular mechanisms of pigment breakdown, or some mechanisms slowed more than others? Um, all of these, as I mentioned, are complex inorganic colored pigments. They're kind of ceramic in nature, and the infrared reflective properties are inherent with the pigments. As the CICPs, as this family in general, these have excellent durability. We did mention earlier that, you know, if you do keep things cooler, there theoretically should be less degradation of the overall system. Um, but it depends on the pigment chemistry from pigment chemistry. Um, so that's the pigments themselves and the resins in there should behave similar to all the other CICPs. Can the story around urban heat island effect be related to IR pigments? Most definitely. You know, you can use these infrared reflecting pigments definitely in roofs, and that's, you know, a large part of the cityscape. But you can also use them in traffic areas, in parking lots, to help have a darker color. You can often have a roof that can't be seen, you know, a flat roof or a low slope roof, be white and be very reflective. But that's harder to do on surfaces where people are walking around. You know, the bright white is often very glaring and hurts people's eyes. So you can have the aesthetically pleasing dark colors and get the reflectivity and reduce that urban heat island effect. And there's new research being done on using these pigments in wall coatings. Um, they don't quite get the solar load that the roofing does, but it definitely has an effect on the building envelope and the air around it. So that's research that's being pushed forward right now. So I'd like to thank everybody for joining us today. I'd like to thank everyone for turning in their questions. Like I said, if you have any questions or are interested in getting some samples for testing in your own systems, please contact us at Shepherd Color, and we'll be sure to reach out to you and get you the right pigments for your application. Once again, my name is Mark Ryan, and on behalf of everyone at Shepherd Color, thank you very much for joining us today.